This is topic 3.4 and 3.5, carrying capacity, population growth, and resource availability. Lots of stuff, unfortunately, in here. So thank you guys for just sticking with me as we go through it. I have a nice little surprise in here for you as well. All right, so we're constantly looking at population size, whether it's human, whether it's rabbits, whether it's insects, whether it's COVID viruses, whatever it is, we're always trying to look at population size. And there are 4 factors that determine how this population size changes over time. It can either increase, and then we're going to look at birth rate. It can decrease because we're looking at death rate. It can also increase because of immigration, or it can decrease because of emigration. Very important we understand the differences between these two. Immigration is how many individuals move into the area. Emigration, how many individuals move out of the area. All right, this is a key word here, and we're going to talk about this a lot, this biotic potential. Biotic potential is the maximum reproductive rate of a species, most importantly, under optimal environmental conditions, assuming it has unlimited food, there's no predators, there's no disease, it can just reproduce as much as its body physically is able to. We're going to look at this as a percent increase per time. So this could be 3% per year or so and so. Or we're going to look at it the time that it takes for the population to double. So is it a 4 years? That means it took 4 years for the population to double. This is all dependent on a few things. First of all, it's going to be the rate of reproduction. So obviously humans, reproduction can only happen every 9 months. Other species have longer gestations or shorter gestations. And then also the number of offspring produced in each reproductive cycle. Again, I think the most that a human has ever given birth to is 7 or 8 children at a time, but normally it's 1 at maximum, maybe 2. Where other species, we know that they can reproduce like wild, so close to 1,000 offspring at a time. So we can look at this based on a comparison of the birth rate minus the death rate. It kind of gives us an instantaneous value. If that value is positive, it means we have an exponential increase in population size, which we're going to talk about later. If it is negative, that means we have an exponential decrease in population size. And a value of 0 indicates there's no change in the population size. Now, humans have a very low biotic potential. They only reproduce a few offspring a year with each cycle, and they can only reproduce once a year. Now, if we compare that to rabbits, we've all heard about like reproducing wild like rabbits. They have a much higher biotic potential, 14 offspring per litter, and they can reproduce 12 times a year. Crazy. A very large biotic potential. Now, I'm going to show you real quick. This is a medium biotic potential. Now, this cutie has a much higher. You can look at me, huh? Sweets. Yeah, you have a much higher biotic potential, don't you? Yeah, because you can have up to 9 kittens in a litter, and that can happen up to 4 times a year. Much more than humans, huh, sweetie? There we go. Okay, so when we have a population and it is reproducing at its biotic potential, remember that means no limits, nothing limiting the rate that it can reproduce at. So we've got tons of food, tons of space, and we can just reproduce nonstop. So when that happens, we're going to see an exponential rate. So this graph here represents an exponential, unrestricted growth. We like to call this a J curve. Oop, that was a horrible. Let's try that again. We like to call this a J curve because it has that very similar curve to a J. And we're going to look at that later. And we have to remember, whenever we see J curve, that means no limits. We're going to look at other instances of that later. And you have to remember, this is all because our rate of reproduction may not change, but compared to here, we have so many more species, even more species, so many more species. And therefore, we reached a lot more species that are reaching that reproductive age, and therefore our total amount of reproduction increases. Now, we know that that biotic potential is not sustainable. Things are going to change, especially as we keep consuming all of our resource. So as our resources decrease, we're also going to see a decrease in that birth rate. So you can see an example here. We have our classic J curve, but then all of a sudden we start running out of resources. And so therefore the rate of births and the rate of population change actually starts to decrease a little bit more until all of a sudden we add a new resource and then we get that classic J curve again. We just have to remember though that there's many different things that can cause the slowdown to happen here. So it could be things like we're lacking resources, predation, disease. All of those things are items that the growth rate is very dependent on. Now, unfortunately, we also know that sometimes a needed resource is diminished. It goes away. And the population that depends on that resource will also start to grow at a much slower rate, or even a negative rate where we have a lot less births than we do deaths. So one great example are bird species that nest in tall, old trees. If a logging operation comes along and is like, nope, we don't need this tree and we're going to take down that tree, then all of a sudden that bird species may experience negative growth because of this lowered fecundity. Fecundity, this is a new word. It's the same as birth rate. So because they don't have their habitat that they need, their biotic potential is lowered a little bit more, and therefore they're not reproducing at the same rate that they were before. So they have a lower fecundity, new word there. Now, as we know, organisms cannot reproduce at their biotic potential. If they did, that means that Korea would be covered with rabbits. We would have rabbits everywhere. They would blanket Korea, all these rabbits. We know that's not what actually is happening though. So it kind of gives us an idea that eventually a population that is growing at its full biotic potential will eventually run into some constraints that will naturally be placed on the rate of reproduction. These constraints result from an increased population size, and they're called density-dependent factors. So that means as my population increases, I'm going to call these DDFs, they're also going to increase. The impact they have on that community is going to have a much larger effect as the population gets larger. You can see an example in here. Again, we have our classic J curve. J curve means we're reproducing at our biotic potential, that exponential graph, but eventually we're going to hit something. And then we're going to start to decrease, and then we're going to level off. And this leveling off here is where we're going to hit our carrying capacity, or K. So as I mentioned before, these density-dependent factors, they cause the population's growth rate to drop as we increase population density. Very important here. So they're going to slow that rate of growth. As our population increases, there's competition for resources, food, shelter, lights if we're talking about plants, And that, unfortunately, is going to lead to decreased birth rate. We're going to have hungry animals, stressed animals that are going to reproduce less often, unfortunately. And therefore will have increased death rate due to starvation, disease, parasitism, whatever happens when we have stressed, starving animals. So super important that we know all of these here. These are the density-dependent factors. They include competition, disease, parasitism, accumulation of waste, which can then lead to disease, or increased predation. So all of those are density-dependent factors. Now, we also have some density-independent factors that can also cause a change on the population size and population growth, but they are not, very important, are not affected by population size. So things such as natural disasters, if you have a tsunami come through, or a volcano, that's going to have a massive impact on the population growth. Sunlight and temperature, due to climate change, we can have changes in that temperature, or if trees grow above them, all of a sudden that could be blocking out sunlight. So another density independent factor. Pollution is another one. And then we see this a lot, oxygen levels. And remember, this is not the fault of the organism. It's just an unlucky thing that has happened that can cause change on the population size. So here's a great example. So over time, we've got our J curve. We're increasing at our biotic potential. And then boom, right there, we have a population reducing event. This could be a forest fire. It could be disease, whatever. Our population is going to instantaneously drop, but then it will recover and we will see more exponential growth. So a J curve, an event, and then another J curve. Okay, this slide is super, super important. So I want to make sure you hold on to all of this, because we're going to look at what do the graphs look like when we do see these density dependent factors affecting our growth curves. So just a reminder, this is growth without limits. This is our J curve. It is exponential growth. So we have nothing that is limiting that reproduction. Now here is another one. This is called a logistic growth. So I want to introduce that to you. It has an S curve to it. Kind of like an S curve there. And this is showing I'm starting with a J curve, but then we're starting to have this inflection point where we realize this competition is too much. These density-dependent factors are causing issues. And then all of a sudden, our rate slows down until all of a sudden, our change is zero. That means we're going to get to this zero population growth, and that is what we call our carrying capacity. This is another super, super important item. Carrying capacity. Yes, the letter is K. That's super weird. It is based off of a German word that we're carrying, starts with a K instead of a C. All right, this carrying capacity is the maximum number of individuals of a given species that the area's resources can sustain without a significant degrading of resource. This is pretty much stating that because of those density dependent factors, our rate of reproduction will always slow down. Our population growth will go exponential, it will hit an inflection point, and then it will start to slow down from there. Now this line here is always shown with a dotted line. It is not a definite line. It can be crossed, and we're going to look at what happens if you cross that line a little bit later. So just remember again, this is our K, and K is the max number, our carrying capacity. It is the maximum number of population size, the largest size that our population can get. So as I mentioned before, we're going to start off with a J curve because we have unlimited resources and we're going to have exponential growth. Then all of a sudden we're going to notice our resources are being limited and we need to slow down the rate of population growth. And then eventually our population size becomes asymptomatic. It just becomes stable and it's not going to grow anymore. We can also look at this in terms of birth rate and death rate. So when we have our biotic potential and we are growing exponentially, our birth rate exceeds our death rate. Then we're going to have this inflection point here where our birth rate is decreasing, our death rate is increasing, and then we're eventually going to reach our carrying capacity where our birth rate equals death rate. Now we can also have these instances where a resource that I depend on is depleted. So let's pretend I've got this tree, I've got purple tree, and I've got the green tree. And I am this beautiful butterfly that likes to eat these trees. So my population at first grows and grows and grows, and then we reach our carrying capacity, and then, oh no, something happens right here. And therefore our population dies off, and then we kind of go back and forth until we meet our new carrying capacity. So in this example here, this point right here represents when all of a sudden, boom, cut that tree, tree's gone. So my resource that I normally rely on is now gone. So therefore my population size needs to decrease to handle this decrease in resources so that we can meet our new carrying capacity. So just to remember that carrying capacity can always change. In addition, we can have this thing happen that's called a overshoot. So again, we have our J curve. It comes up, 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 up. Ooh, we've passed our carrying capacity. We have overshoot our carrying capacity. This is when our growing population temporarily exceeds the carrying capacity. This could be due to a lag in time between the depletion of the resource and the resulting drop. But over time, we will see that eventually we're going to settle. It may require, when this happens, when we have our overshoot, we're going to have an automatic dieback. And this here represents the dieback. Now, then all of a sudden they're going to notice, hey, we have a lot of this resource, so we can grow again. Then we'll die back. Then we'll grow again, die back, and so until eventually it figures out its carrying capacity. This is often kind of what predation looks like, so I'm going to show you an example of that as well. This is another great slide, just again reminding you this is what our J curve looks like with our exponential growth. This is what our S curve looks like with our logistic growth when we're taking into consideration those population dependent factors. All right, I mentioned I was going to talk about the prey population and how we can have these sine curves up and down with the prey population and the predator population. This I find is really interesting, that the populations are going to fluctuate around that carrying capacity as a result of predator-prey relationships. So bear with me here. I have a ton of prey at this point. And so that's going to cause my predators to increase. But now they're going to increase so much that my prey is dropping. And as this prey bottoms out, this population also decreases. Well, because we have a decrease in the predator population, this population is going to take off again. So therefore, our predators also take off. And it's just this very cyclical pattern that we notice between predator and prey. But very important here is that they're going to be offset from each other. So this is the peak of this wave, and this is the peak of this wave. So just keep that in mind. Now, this overshoot can lead to really catastrophic collapses in the population. When we overshoot, we're also often going to receive starvation, disease, and conflict. So sometimes we can overshoot too much. When we overshoot too much, we can have the whole population completely collapse. This is a great example of this. This is the reindeer population on St. Matthew's Island. What they did is, this was during the war, this is during World War II, and they wanted to provide like a Christmas experience for the soldiers. So they put all these reindeer on an island. We've talked about island biogeography, so it was a very uninhabited island. They put all these reindeer on there, and they just thrived. Look, if this is our carrying capacity, we had a beautiful J curve, and then boom, all the way up. They completely overshot their carrying capacity. So they released, I don't know, you could say maybe 10 to 12 back in 1944, and then they came back in 64. And look, there's 6,000. Oh my goodness. Completely overshot their carrying capacity. And because of that, they ran out of all food. There was no food on this island left at all, creating a complete collapse. I just wanted to show you this. This is COVID, and it shows the COVID cases in the first 1, 2, 3, 4, 5-ish months. And you can kind of look at this idea of overshooting a carrying capacity. Here is our J curve right in the beginning. And then all of a sudden we hit this peak and then we start dropping again. Most likely because our carrying capacity is probably right around here. So the COVID virus overshot its carrying capacity, and then we had a dieback that happened due to that increased competition. Then it dropped below again, and then it raised again. So just interesting to see this in something that we're very familiar with. All right. Fantastic. Hope you all enjoyed.
What a sleepy kitty.